Hello, for those of you that don't know me, my name is Miss Carraro, and I'm going to be going over differentiability at a specific point in piecewise functions. So to get started, something that we need to remember is that a function is only differentiable where it's continuous. So our functions must be continuous in order to be differentiable. But there's some examples where we can have a continuous function that's not differentiable at specific points. And that's going to be when we have sharp turns or when we have a vertical tangent. So that's some background information that we need to have in order to do these couple of problems. So let's get started. So this first example that we have here, I have a piecewise function, so f of x equals this broken down into two pieces, and it says if f is the function defined above, then the derivative of f at -1 is what? So this is telling us it's defined, but that does not mean that it's necessarily continuous, especially because at -1 we have that sort of breaking point for the piecewise. So first we need to make sure that it's continuous at -1. So we're going to start with our rules for continuity, where step one is to make sure that f is actually defined at -1. So we're going to choose the bottom piece of this function. So f of -1 is going to be to plug -1 into that bottom equation. And the reason we're choosing the bottom equation is because we have that or equal to right here. So that's what tells us that this is the one where the function actually includes -1. So we're going to get -1 plus 3, which is positive 2. So f is defined. That's great. Step 2 of our continuity is to make sure that the limit exists at that spot. Now, because this is piecewise and -1 is that breaking point, we need to check both the left and right-handed limits. So we're going to do the limit as x approaches -1 from the left, and that's going to be to look at this top piece. So I'm going to plug in -1. We get -3 plus 5, which is positive 2. So the left-handed limit exists. So let's check about the right-handed limit because it needs to be the same. So again, we're going to use that -x squared plus 3, which we've already calculated before, and that gets us 2. So for our continuity check, we need to have both the limit existing and we need to have the function defined there, but we also need these things to equal each other. So f of -1 is equal to the limit as x approaches -1. So we're good because 2 equals 2. So it's continuous. We did all that work and all we've proven is that it's continuous at -1. We have to now find the derivative at -1. So we're going to have to find the derivative of both halves of this piecewise, and that also needs to exist. So let's check the differentiability for the left half. So if we differentiate 3x plus 5, we get 3. And if I differentiate the second part here, we'll get -2x. So let's check at -1. We're going to get positive 2. And then for our left side at -1, it's still just going to be 3. So if I'm checking the differentiability here, at -1, these two things need to be the same value. It needs to have the same slope at that point in order to be differentiable. And so in this case, because 3 is not 2, this is actually not differentiable at all. All right, let's move on to example number 2. So we have another function given, and it says it's defined above. Which of the following statements is true? And I'm scanning through these answer choices, and they're all about being not differentiable. So we're going to have to go through that same kind of process that we did for number 1, but we need to actually figure out why is it not differentiable, because we know that it's not. We just need to say, well, why is it not? So let's start with our continuity. So in order to be continuous at 5, I need to check first what f of 5 is. So we're going to use the bottom piece because that's where it is actually equal to 5. So I'm going to plug in 5, and I get -25 plus 20, which is -5. So it is defined at 5. We do have an actual value here. So for our answer choices, Option D says it's not defined. That's out. So let's go and check part 2 of our continuity, which is going to say let's do the limit. All right, so let's get into the left-handed limit here. So we need to do the limit as we approach 5 from the left. So that means I'm going to use this top function and plug in 5. So we get 25 minus 20. So the left-handed limit is 5. And we essentially found the right-handed limit a second ago when we did f of x, but let's double check. So the right-handed limit is going to be negative 25 plus 20, which is negative 5. So here, our limit actually does not exist because we have two different values for the left and right-hand side. So if the limit does not exist, it is not continuous. And if it's not continuous, it's not differentiable. So let's go check our answer choices here and figure out which one is going to be true. So option A says it's not differentiable because it's not continuous. So yeah, we kind of just proved that because the limit does not exist, that means it's not continuous. B and C are both talking about sharp corners and vertical tangents. Those would only happen if it's continuous. Since we've already said it's not continuous, those are also going to be out. But we always want to double check all of our answer choices when it's multiple choice like this. All right, so let's get into number 3 now. So I want you to actually pause the video for a second, give this problem a try, and then check back in and see if you got what I got. Okay, so as before, we are given all of these options that talk about being not differentiable. So let's start by checking continuity and figuring out, is that why it's not differentiable? All right, so let's start with our continuity. F of 5, we're going to use the bottom piece of this. And I get 10 minus 4 is 6. Okay, so the function is defined at 5. So let's go through these options. Option D says it's not defined. That's untrue. We did get that it was defined. Option D, that's not actually written. Let's pretend it's written. All right, so it is defined. Let's check the limit. I'm going to go over here. So the left-handed limit as x approaches 5, we're going to use the top piece for that. So limit is 2. Fantastic. Let's check the right-handed limit. These two things should be the same. Now I'm going to use the bottom because greater than is going to be to the right. So if I plug in 5, 10 minus 4 is 6. Okay, so the limit does not exist. And so again, that means that it is not differentiable because it's not continuous. Because if the limit doesn't exist, the function is not continuous. Just like with problem 2, B and C are assuming it is continuous because you can only have a sharp corner or a vertical tangent if you're continuous. All right, so we've got one more problem on this page, and let's just kind of reason through all of these because it's not so much a doing of math, it's more of a thinking conceptually about this. So the problem says for any function f, which of the following statements must be true? And the word must here is really important because sometimes it could be true, but doesn't necessarily have to be true. All right, so option 1, if f is defined at x equals a, so we do have a closed dot at a, then the limit as x approaches a of f of x must equal f of a. So sometimes with problems like this, it's easier to think, well, can I envision something that is defined at x equals a, but where this part is untrue? And if I can figure out like a non-example, then this does not necessarily have to be true. So can I have a function that is defined, but where the limit is not the same as the function? And absolutely, if I have something with a removable discontinuity, then we would have the function is defined because the dot here does exist, but the limit would be approaching something fully different. And so those would not be the same value. So we can eliminate option 1, not necessarily true. All right, option 2 here. If f is continuous, so that's important, at x equals a, then the limit as x approaches a of f of x is equal to f of a. So this is actually that third step in our proving of continuity. So remember, step 1 is does the function exist at that spot, or is it defined at that spot? Number 2 is, does the limit exist at that spot? And then 3 is, those two numbers must be the same. So yeah, if it's continuous, this absolutely has to be true because this is in our proving formulas. So this one, yes. And then option 3 here says, if f is differentiable at x equals a, then the limit as x approaches a of f of x equals f of a. So as I said at the top of this video, if you are differentiable, you must be continuous because you can't be differentiable if you're not continuous. So since this again is part of our continuity proof, if it's differentiable, then it's continuous, and if it's continuous, this is true. So that means 2 and 3 are the only correct answers here, and that is it.